Vivek Ponnada. I am, so it looks like the slides are available. So let me just share my slides. Okay. Is it working now, Ashley? Okay, perfect. So we'll continue. So quick background. I've been in the industrial control space all my life. I've been doing OT security for the past 8.5 years. By background, I have an engineering degree and also an MBA in finance and a SANS cert for industrial control. So when I'm talking, usually I talk with a big bias towards operations technology and in general ICS space. So currently I work for Nozomi Networks. I'm the regional sales director for Western Canada. I'm based here in Vancouver. And some of you know me from my participation in the community here in B-Sides, as well as ISA and ISACA. And I also happen to co-lead with Sarah Flukes, the Top 20 Secure PLC Coding Practices project. So the interesting discussion for today, right? Quick peek at the agenda. So air gap was a thing. So we'll go a little bit deeper into what that was and why it isn't valid anymore. And then let's talk about Purdue Model and things that break the Purdue Model, and then reality check about where we are. So these pictures should tell you a good story. So on the left, you see a big piece of equipment. It doesn't matter to you what that is. It happens to be a steam turbine producing power. But if you look at this picture, this is actually from the early 1900s. So 100 years later, if you walk into a turbine hall, the equipment look very similar. So the technology kind of evolved, the metallurgy evolved, the temperatures at which we run these things evolved, the amount of megawatts it produced evolved. A lot of things kind of evolved, but they look very much similar. So the key difference is back in those days, these sensors were all local. So if something was measuring pressure, you would display the pressure on this indicator here. Something was measuring temperature, it would show up on the gauge right there for an operator to go and troubleshoot and click on things, right? Adjust levers, adjust valves, anything that was local, right? So that's all localized control. And then eventually now, most of this control is done by programmable logic controllers, PLCs, the picture that you see at the top right here. And the sensors too have evolved. So here you see a pressure transmitter. So the fitting here, the tubing, that hasn't changed in 100 years, or actually hundreds of years, but the thing at the top definitely evolved. So that's all digitized. You see this local indication, but it also communicates to this programmable logic controller over wires. So usually 2 wires that go in here, physical milliamps, 4 to 20 milliamp signal goes to the PLC, and then 4 to 20 milliamp output also goes to a valve. You see this valve, this is a globe valve. This hasn't changed in hundreds of years. However, it now has a smart positioner at the top. So this smart positioner not only does control of the valve position, but also gives you indication about if the proximity switch that's showing the open or closed feedback is faulty, or if the valve calibration is out of whack, meaning the zero position, the max position, if they are not exactly what they should be. This smart positioner can adjust it. You can calibrate the valve. You can stroke the valve, meaning move the valve position from remote. So those are the additional features we got with these introductions of smart features. And this has nothing to do with our smart 22nd century thing. These things happened in the late 1900s. So the sensors got smarter, the end devices got smarter by tacking on things to something that already worked for 100 plus years, okay? Now, the picture on the left, I don't know if you're able to see it clearly here. It's showing black on my side, but maybe that's well worth it. So picture on the left was supposed to be an older control room, okay? The older control room, the operator had limited view, but they still had a view. They had data recorders, they had slides, they had paper charts, they had a big red button to push in case something was wrong. It looked very messy because you needed direct connection from these sensors and outputs to the actuators in front of the operator. But then to the right, where now the operator has a lot more view, right? You see all these displays, all these video screens where they can see live animations of where the process is, what pipeline has what temperatures, what product, what pressures, what furnace is burning at what temperature. All those things the operator can see on a display, right? And they can choose to rearrange, they can reorganize, they can monitor the process much better. All the data is now in front of the operator versus before when it was a struggle to pick and choose what was available. Okay. That brings to the most famous OT model that you'll ever see out there. It's called the Purdue Model. And I say that's the torchbearer in OT because that's what we use as a reference. Whenever we see OT equipment, we say, where does it line up in the Purdue model? This model goes from level 0 to level 5. And I put the same picture so that you can relate to them. So at level 0, you have these sensors and actuators, right? So the pressure transmitter that we saw in the previous picture and the valve and the smart positioner that we saw in the previous picture would be considered level 0. There is some kind of processing, some kind of data historically, like in the 60s, 70s, 80s, in the 20th century, it was strictly milliamps and volts. But since then, we added different protocols that can bring in additional data, like HART protocol, different field bus protocols that now have more data. So you can now configure the transmitter to say this transmitter would be called PT01 in section 1. Or you can configure this smart positioner to say this is valve 2001 controlling some kind of ethylene equipment, right? So you can do all that stuff at level 0. At level 1, you have these controllers, programmable logic controllers, distributed control systems. And then at level 2, you have this user interface, right? Operator interface or engineering workstation that you use to download programs to the PLCs. And the operator, again, same picture, so you can see how that lines up in the Purdue model. Now, air gap, as we hear about it, came in because back in the day, back in 19th century, early 20th century, even late 20th century, all these things were limited in connectivity. So the amount of data that went from 0 to 1 was strictly limited to whatever the sensor information was and whatever the valve output needed to be from the controller. And the most they traveled was to this level 2. And there were no switches back in the day because this was not Ethernet. This was not the regular IT protocols that we're familiar with. These were all proprietary at the time. So there were some connections, but most of the data was limited to this. So the level 2 and above were disconnected, meaning if you were in the plant and you had email, let's say in the 1990s, you had email obviously at the corporate level. You had other systems managing inventory, looking for billing, things like that. Those were disconnected from this process network. So while air gap is a technical military term, they applied that in OT saying, hey, this section is disconnected from the rest of the IT network, so let's call it air gap. So it kind of made sense, right? And because of that, the risk to the OT network or the risk from the OT network to IT, vice versa, both of them was limited because you were not physically connected. These things were not connected to the IT network. Now, in this newer model, where everything is connected everywhere, there's a reason and purpose for that, right? Because the data here is rich, is useful, is beneficial for a lot of things, it started being connected to the IT network. So in this reference base case model, what they're saying is you have a DMZ where you terminate things from the internet, and then you separately authorize and authenticate data coming from OT, because most of these OT networks have obsolete systems, unpatched systems, unsupported systems. So this architecture, if you build it a certain way, if you build it with security in mind, you would have a DMZ and you'll have firewalls with specific rules to allow for specific access, specific type of access, specific protocols. All that is in theory, right? So this Purdue model is in theory how it would work even if you have an OT network that's, fairly insecure. So that's the concept. And again, the reason for connectivity is you have production systems, you have inventory management, you have billing. If you're a pipeline company, for example, that want to know what product is actually in the pipe right now and how much you're billing your end user, that information is at this level 0. So for that information to be used for billing or to be used for something else, for inventory management or for bidding on the next megawatt, you need that information in your IT systems. So how do you get there? Is to have some kind of implementation like this where you have firewalls in place, you have routing, you then have a DMZ where you terminate the connection and then have someone else from IT, from internet access, get to the DMZ and collect the information. That's the idea anyway, okay? However, things that break the Purdue model. So by design, if you have an IoT device, whether it's a audio or video recording device, including drones that are used these days to collect information. For example, if you want to inspect a top of a stack, for example, you send a drone up there, and that drone is collecting information about the status of what it's visualizing, but it might also have a 4G or a 5G modem, right? Or if you have smart sensors for data collection. Now, if you have a pipeline pig that's collecting information while traveling through the pipeline, or if you have other sensors that collect information about the weather, because that's what you're using in your process. If you're a transmission distribution company, this weather-related sensor is important because you might want to dispatch people or personnel in advance where you're expecting some kind of tree fall, right? So that you can clear the shrubs, have less of an outage window. Or if you have other barcode readers or any of the other IoT devices that are proliferating everywhere for good reason, they have these modems built in. So that breaks the Purdue model because now all the data is not strictly going into level 0 to level 2, but it's directly connected to the internet. Same thing with PLCs. We have now PLCs available with web server and 5G modems built in, which completely breaks the Purdue model because now the level 1 device is directly able to access the internet. And then by dependencies, right? So if you have a vendor that you need support with on some operation of your gas turbine, for example, and they need to be able to log into your HMI, the human machine interface, to be able to help you troubleshoot or maybe optimize some of the operation, they typically have some kind of remote access to your HMI. Now, you can do it properly, securely through the DMZ, or like in most cases, the vendor has only one tested way of doing it, and that's a direct connection to the user interface. And then in other cases, by practice or by errors, right? So maintenance personnel accessing the engineering workstation from the office network happens all the time. So they bridged without the DMZ directly their level 5 network to the level 2 engineering workstation, or maybe some other process optimization inputs that have direct access to the HMI. Again, this happens because you're trying to optimize something with information that you have in level 4 or level 5, and you now have direct access to the level 2 in the model. And then billing and ERP systems that are able to write to the HMI as opposed to only reading, right? Because if you have a firewall and it's all based on rules, right? So you might have a bad rule that then says, not just reading, but also enabling write. Similarly, undocumented external connections. This happens all the time. If an operator connects a cell phone to charge on the HMI, suddenly has created a bypass to the HMI, right? And then misconfigured firewalls. We talked about one before. Misconfigured routers happens all the time. In my line of work, I see this all the time where people think they have no connections. They say, oh yeah, we're air-gapped, we're disconnected. And next thing you know, you do a passive ingestion of packets on the network. You realize they've had so many external connections that were not documented. So by all these problems, the Purdue model is broken, right? So the theoretical model never was true in the first place, but even if you had this idea that you have this plan built in with the Purdue model in place, it's still broken because of all these things. Next up, industry trends, right? So these are the other aspects of, the cloud is here to stay piece. So digital transformation, cloud analytics, we all know in our IT world, we know how much of a benefit we got from these cloud analytics projects, right? Same thing in the OT side. A lot of end users are leveraging these transformation projects to connect more things. So you need more data, means more connectivity, and then significantly faster and inexpensive projects leveraging IoT. So if you were to connect a sensor in the traditional way, right, lay new cable, lay new hubs, lay new everything just to get a piece of information from a remote tank farm onto the level 0 network to level 1 to level 2, that sometimes costs you millions of dollars versus putting a sensor out there that has an IoT capability, bring it to the cloud. you're just done with a couple $1,000s, right? So significantly different economies of scale leveraging IoT, which means even more cloud application in OT. And then retiring experienced professionals. Sometimes you hear this thing, oh, in the past, we were able to run this in manual. In the past, we did not need internet connectivity. Oh, even if our IT side is ransomware, we can run OT manually. All that is gone, right? So the experienced professionals that could do it manually have retired or are retiring, or the tools that were in place, the methods, the processes in place that were able to cause this manual operation don't exist anymore. So you can't go back. I mean, this is one of those things where the wine is being uncorked, you can't put the cork back. And then risk analysis, right? It's meaningless for organizations now that cloud is here to stay to focus just on IT risk. The business risk is the key, right? At the end of the day, you have to figure out if the incident, whatever that might be, happened and happened to cause any disruption to your primary business objective. It caused any production loss, yes or no? That's the only important piece, right? As far as the production is concerned. And then if there was any unacceptable impact on personnel health, safety, or environment, this has always been the case with OT, right? OT, essentially, every time you think about OT and industrial control system, you're thinking personnel, health, safety, and environment. So that hasn't changed. So if there's an impact to that, you got to look for risk analysis and risk mitigation for that piece. So clearly, ransomware affecting only IT systems and OT systems not under being attacked, that's just irrelevant. The key thing is to figure out if your business is at risk because of this increasingly applying cloud and IoT in the OT space. And then actions, right? What you have to do in OT is slightly different from what you do in IT. In OT, you have to still identify all your assets. Most OT places don't have asset information, asset inventory. They don't have a good asset management structure in place. You have to start there. You have to then assess your vulnerabilities and then monitor the risk, right, over time, detect any anomalies and detect any threats in your environment. And then this is another key aspect. In IT, you're used to, let's patch up things. As long as you're up to date, you're in golden shape, right? But that's not the case here. In our case, we not only have to think about reducing likelihood, but also have to think about impact. So if something wrong were to happen, how can you limit the worst case that can happen? So if you know of a furnace that can go, boom in case of an OT impact, you have to figure out what other physical boundaries or whatever physical ways you can cut off fuel, for example, to limit the impact, right? I know we're going slightly over, so let me make it quick on the last slide here. So final thoughts. All the things that I mentioned in the previous slide about how cloud connectivity, analytics, and everything is here to stay, and you can't undo it, right? And how you start with the asset discovery, asset visualization, all that is step one. I mean, thankfully, that's a good step that collect a lot of information, rich information for you to use going forward, but you still have to go through these other steps. You have to still go through personnel training, right? Still leveraging industry groups. So if one industry, one vertical has a main attack vector, leverage that for the others in the industry, establish a disaster recovery policy and a recovery time objective. And this is crucial. Like if you're talking about fire, right? So most of the OT installations historically have had great plans for fire, but because fire is something you don't really plan for, right? You say, hey, in case of a fire, we throw all our resources at it, bring the community resources, bring the water, bring the fire personnel, everybody, but you don't plan for rebuilding right away because that's not how those extremities work. Whereas in our world, you have to build resilience. Like you have to be able to constantly adapt to say, I'm expecting this kind of cyber attack, whether it's ransomware or something else, and how do you get back up really quickly, right? For that, you have to do tabletop exercises, incident response exercises, and then obviously you can't outsource every one of your incident response scenarios, but you have to have a retainer with someone, right? You have to build your own personnel, but also have a retainer with a third party. And then once you have an incident, post-incident management, that's crucial, right? Think about a ransomware situation. Some countries are making it illegal to pay ransom. And then unlike in IT, right, you can't just come back up. It's not like you can reflash an image or restart a container. Like in our world, you have to rebuild everything from scratch, which means that sometimes even if the recovery key works, it might take months for you to come back up. So you have to have a recovery time objective for coming back up in a much quicker fashion, right? whatever is applicable for your industry and for your company. So there's a lot more to our OT world where cloud is increasingly everywhere, prevalent 100%, right? A lot more IoT for sure. The air gap that hasn't existed in more than 2 decades, people still keep talking about it. So when you hear that, tell them air gap is myth, doesn't happen anymore, and cloud is here to stay. With that, I will end and take any questions.